Thanks for introducing me. This talk is a joint work with François Le Gall, Harumichi Nishimura, and Qisheng Wang. So I'll begin by explaining the meaning of each word in this title. And particularly, I will say something basic about quantum computation to refresh your memory. So when we talk about quantum computation, classically we talk about bit. Quantumly, we talk about something like qubit. It's a two-dimensional vector, and like the coefficient is normalized. And right, so of course, the computation not just happen on a single bit. So it happens on like on an n bit. So in quantum case, we'll talk about the n qubit. And in that case, it's an exponential dimensional vector, and also everything is normalized. So here is something like a rank one case. And in general, the quantum state could be something have a very high rank. So then in that case, the n qubit quantum state just 2 to the n by 2 to the n positive semi-definite matrices. And of course, it's normalized. And in this sense, normalized means that trace is equal to 1. Once we have the quantum state, we want to do the computation. So classically, we can apply something like AND or NOT gate. Here is, so we're just applying this elementary quantum gates to just the 2, 1, or 2 qubit unitary matrices. And at the end of the day, we want to read the result. And particularly, usually we talk about decision problem. So we need to measure some desaggregated output qubit. And basically, this projective measurement will collapse the result to either 0 or 1 with some probability. So now basically we can define what is PQP in the usual time-bounded computation setting. So here the computation is using a polynomial number of elementary quantum gates that trivially requires a polynomial number of qubits. And the whole computation can be, the description can be computed by a deterministic polynomial time-turing machine. And the goal of such computation usually is really to find a very small corner of a huge Hilbert space. And to do so, we cannot really like check the entries in that huge vector or matrix. So instead, what we do is do the measurement to extract the information. That's a very basic thing about quantum computation. And one important subtlety in this work is about something called intermediate measurement. So this measurement was slightly different from the previous one. So particularly here, we're talking about a measurement implemented by something called the pinching channel. This channel, think about like 1 qubit case, just remove all the coherence. Then after the measurement, only the diagonal term lived in the post-metric state. And this kind of intermediate measurement turns out it's not really helpful in the usual time-bounded setting. Particularly, we have something called principle of deferred measurement. So basically, each intermediate measurement in the middle, we can replace it by control NOT gate with a new ancillary qubit. And then in the time-bounded setting, usually we have most polynomial number of the steps. So it's enough to replace everything by using only a polynomial number of ancillary gates. Sorry, qubits. But it's not the case for the space-bounded setting. So for space-bounded quantum computation, particularly, I'm referred to this model introduced by John Watrous about 25 years ago, a class called BQL. Here, the difference is computation still requires a polynomial number of gates, but everything happens on a logarithmic many of qubits. And also, the description of the computation can be computed by a deterministic log space turing machine. So since everything happened only on like log qubits, so essentially the matrix underlying the quantum log space computation just a polynomial dimensional and looks everything actually is a bit easier and it's containing NC, in fact in NC2. But one important subtlety here is this principle of deferred measurement technique does not work in the log space setting. So it may suggest that the intermediate measurement have some power. Right, even this class looks a bit weak. Actually, still it have notable power and recently gained some attention. So when John was defining this model, he also showing that we can simulate in quantum log space. In the deterministic space is log squared. And about like 10 years after that, Tashima find an example, which for this inverting well-conditioned matrix problem, the best known classical algorithm indeed requires a log squared space. But on the other hand, we do have a quantum log space algorithm. Of course, at the beginning, you have to use intermediate measurement, but a few years later, Furman and Lin is showing that actually this problem is complete for the class, even we don't need to use the intermediate measurement. And so basically, it's a rise of question about like, is this intermediate measurement is really helpful in a log space computation or not? And so it's a principle of different measurements. If there's only like a few number of intuitive measurements, so still we can introduce ancilla, and it's not powerful. And beyond that, it was a long-standing open problem for about like 2 decades until a few years ago. Furman and Ramscram, also the other group, Rich, Schwartz, and Jen, is showing that even allowing like polynomial number of intermediate measurement, and also there's even reset operation. I mean, you can reset the qubit to be 0. Even for that case, if we only talk about a promise problem, then there's no advantages. I should emphasize that actually this technique does not apply to the setting like the state synthesis setting. So if we have like a log space quantum circuit to prepare like log qubit states, then if it's preparation circuit using intermediate measurements, then this technique actually cannot really show construct another unitary circuit can do which achieves the same thing. So last thing I would say is in quantum log space, actually we have several techniques to show to design an algorithm. Even this very powerful unifying quantum algorithm framework have a log space. This quantum singular value transformation can be done in log space. It's based on our first work with François and Qisheng. And a particular example here is about like space-bounded quantum state testing problem with respect to the trace distance. And in Water's paper, which introduces a quantum statistical Zara knowledge, he also implicitly shows that this problem is contained in NC. But on the other hand, we show this problem is BQR complete. Actually, also a corollary in this work is we can show a space-bounded variant of quantum statistical Zara knowledge, so particularly the verifier only using like unitary gates. In that case, it's contained in BQL. So we kind of a spoiler of the side result. Now I move to explain what is interactive proof. I guess it's very standard for most of people here. So particularly here for coherence, we talk about the promise problem, and then there's a proof system. There's a prover, it's all powerful, untrusted, and the verifier is usually like bounded power and can use randomness. There will be messages exchanged between the prover and the verifier. So the whole proof system just for yes instance, except with high probability, for no instance, except with no probability. This kind of model is introduced by Babai and also Godwasser, Mikhaili, Rakov about 40 years ago. So one interesting property here is if the verifier are only able to ask random questions, and then turns out such model is as powerful as asking the clever questions. So what I'm referred to as random question is just the verifier toss some coin and use it to directly ask question. It's something called public coin. And the clever question means that the verifier can use whatever the witness in the way you want to use it. And it's something called a private coin. And if the proof system only using like the constant number of messages, then turns out everything is collapsing AM. Actually, is contained in polynomial hierarchy. But on the other hand, if there's a polynomial number of messages, then actually it's verified the p-space computation. Now I move to the quantum interactive proof. So the setting actually is very similar. We still have an all-powerful prover, and now the verifier is can do quantum computation. So the messages exchanges between the prover and the verifier, they're quantum. And also, even at the beginning, there's no entanglement between the prover and the verifier. The entanglement could be created doing such interactions. It's kind of like this picture drawing by ChatGPT. And similarly, we have this threshold. So this model is introduced by Kitaev and Wojtos. The one, I will say, the most striking property of the quantum proof system is any quantum proof system using like polynomial number of messages, we can construct a new proof system using only 3 messages. It's something called parallelization. But on the other hand, it took people about a decade to understanding really the power of such class, and turns out IP is equal to QIP. So now I try to say something not standard and put space-bounded and the interactive proof together. So this space-bounded classical interactive proof was introduced by De Worker and Stockmeyer, also Annie Condon, about like 35 years ago. So one interesting and important subtlety here is, unless in the time-bounded case, here the public coins will weaken the power of such proof system. So particularly if we're talking about the classical interactive proof system, use a log space verifier and private coins. If we only use like log n private coins, Cardone and Lerner showing that this model, in this talk we call that IPL, can exactly characterize NP. On the other hand, if we use like polynomial number of public coins, turns out the model is exactly characterized P space. It's also shown by and Cotton, and I think both of the paper was a conference version actually is in accepting CC. But on the other hand, if we only talk about like public coin case, then in any Cotton's PhD thesis, it shows that if we only use a polynomial number of public coins, then the whole proof system is containing P. But on the other hand, the lower bound seems a bit harder. In Lens-Fussenot thesis, he shows that use log n public coins, and we can verify like computation in SAC1. So here is S just means that semi and this fan is AND gate have a bounded fan in. And it took about another 2 decades or even longer. This famous GKR protocol also showing that if we are using log n public coins, then this clever use of a sum check protocol actually can help us to verify any computation in P. So in this work, I will try to define a quantum analog of such models. So particularly here, we refer to something like a direct access, means that whatever the prover sent to the verifier can just process it directly in its workspace qubits. And this kind of model was previously considered in the setting we only have one message. So it's something defined called QMAL, like a quantum space-bounded quantum analog of MA. And turns out this model is fairly weak. Actually, this message was not really helpful, and the proof system is just as powerful as PQL. Now I'm going to move to define such a proof system, and there will be several subtleties. So our first attempt is try to do something exactly same as the time-bounded case. So we define a space-bounded unitary quantum intelligent proof system. So here, even the picture is just looks the same as the one in KDAP virtuals. So here, the very first action only can use a unitary quantum circuit, and both the message register M and the very first privilege register W, they only can use log n qubits. So that's the meaning of space-bounded. And another subtlety is here we require some kind of strong uniformity, means that the description of each various action can be computed by a single log space Turing machine. So this kind of subtlety is only happens in space-bounded setting because in time-bounded setting actually is equivalent to a kind of a weaker notion. But this model is not that strong. Actually, it cannot contain this IPL model defined by Connor and Lerner. The reason is, for instance, you want to show IP is containing QIP. The soundness actually only against classical messages. So to use this soundness directly, the verifier really needs to measure whatever the messages received from the prover at the beginning of each round, which requires a lot of measurements, and this cannot be done in this system. So the takeaway here is the soundness against classical messages actually does not trivially extend to quantum, particularly if the verifier only can use unitary quantum gates. So we are looking for something stronger. This leads to our second model called space-bounded isometry intelligent proof system. So here the verifier essentially can use whatever we can use in the quantum log space, meaning it can use not only like log n intermediate measurement, but also log n reset operations. So this model, of course, contains quantum Leitner that appears too powerful. So the prover and verifier can do something like that. The prover can send a very long state by like an n-qubit state by n log n segment, and each segment just log qubit messages. Of course, the messages could be entangled. And verifier need to do is only choose like a few number of qubits from this very long state, and then do some computation. Of course, the prover don't know the choice of the verifier. So if you know this local Hamiltonian problem, kind of quantum analog of maximum K set, and turns out this simple protocol actually can verify QMA. So it looks too powerful. So our actual definition is looking for something even a bit weaker. So here we call this very first action as like almost unitary quantum circuit, means that it's a unitary quantum circuit and also can use log n intermediate measurements. We also define something called QPLHC with a high concentration condition in the yes instance. So intuitively, this condition actually can be interpreted as the prover's messages is almost classical in the for the yes instance. And it's easy to see that both QIPL and also this QIPLHC, they contains this IPL model. So they are powerful enough for our purpose. And now I'm going to say the main result of this work. So the first result is characterization of a QIPL, particularly we're showing that there's equivalence between NP and QIPL HC. So this QIPL HC basically is the weakest model that includes this space-bounded classical improved system introduced by Kondo and Lerner. And also the technical challenge here is in a time-bounded setting, we only need to think about a case which the verifier is only can use unitary gates, but it's not true in the space-bounded case, which means that we need some new technique to upper bounding such proof system directly. Our second result is the characterization of this QIPU proof system and even works for the case with polynomial precision. So the lower bound is just the SEC1 union BQL and upper bound is P. So basically, that's the main takeaway of this work. So assuming that P is not equal to NP, then we know intermediate management could really make this model much more powerful. So QIPUL strictly continue QIPL. The third result is if we talk about like the constant around proof system for all these models, and also the promise gap is large enough, it's constant, and turns out everything is contained in NC. So actually, all the three models I mentioned in the last session, they are refers to the same thing in this setting. Say something about proof. So first is the upper bound for the unitary verifier case. And here, basically, what we need to do is just examine all the known techniques, and some of them can be adapted in the log space setting, and the other cannot. So the first step is we try to do this parallelization thing for the QIPUL proof system. So the original approach by Kidaf and Woodruff actually does not work. They require to send kind of like everything in the message register and also verifier register together. Since there are like polynomially many number of the messages, and then if we combine everything in the same message, then it's too huge, it's too large, it's like polysize. So instead we use another approach, we call that turning half approach. It's kind of a dequantized version of the above one. So this approach is, they have like a new proof system. It's the prover sends something in the middle of the original proof system, and the verifier then tosses a coin to go either forward or backward, and to check the protocol is ending the right way or starting the right way. This requires that the verifier's action has to be reversible. Moreover, we want to apply this procedure recursively several times. So it's also required the verifier's action should be like the dimension preserving. And this two restriction means that all this approach actually only works for the unitary verifier case. After that, we can try to adapt the standard SDP formalization for QIP. And particularly here, we're talking about like constant message proof system. So the solution of such a SDP program is have polydimension, like corresponding to like log number of qubits. And then we can just solving the SDP program using standard SDP solver. So basically, the takeaway here is for the QIPUL model, this quantum property, this parallelization makes everything easy. And when the gap goes to be very large, turns out it's just exponentially downscaling version of this QIP equal to P space result. But if we're talking about like non-unitary verifier case, then things goes to be a bit complex. So here particularly, we define something called the omega VU, which denotes the contribution of some particular measurement outcome branch. So this U just just like the union of all the intermediate measurement outcomes in each verifier action. And yeah, this notion is just a contribution of such approach to the maximum acceptance probability denoted by omega V. And one thing good about this pinching measurement is it only Q the coherence between the subspace corresponding to different branches, which means that we can actually dealing with this omega VU like independently and approximately. And because of that, so there's still some hope to use SDP to get some upper bound. Turns out for any fixed branch U and for any proof system, we can still write an SDP where the constraint there, some subtlety, is not really the same one used in the unitary case. And this SDP will verify approximation hat omega VU of the original one, and it kind of lies between the actually the contribution of this branch in the optimal proof strategy, and also cannot be larger than the optimal proof strategy. The reason for the lower bound is because this SDP actually is just maximizing everything in this particular branch. So there's no constraint about like check the consistency. But on the other hand, the global proof strategy, I mean, consistent with what happened in this branch actually cannot better than the largest one. And once we have that, we still have a SDP, and this SDP have a good property, means that the solution can be write a Cartesian product of a polynomial number of like log qubit states. And so like we can verify it's in NP, but on the other hand, like the solution here is still using a polynomial number of qubits. So if we just use SDP solver, then there's nothing good happens. So that's what happened for the upper bound. For the lower bound part, if we talk for the unit for QIP URL case, what we want to do actually is quite easy. We want to simulate like a classical proof system using log n public coins. And to do that, we only need to do like log n intermediate measurement in the middle. Even we're talking about like unitary verified, but still we have like log space, so we can do that. Then the lower bound actually is inspired by this classical protocol in Lance Fosnot's PhD thesis about the SAS1 circuit. On the other hand, the upper bound for the lower bound for the QIPL is a bit tricky because we want to simulate log n private coins in the classical proof system. So this means that since it's private, we need to make sure that the prover really cannot know what's happening in these coins. So it's not enough just simulating these private coins and exactly using the intermediate measurement. The verifier also need to measure each message recepted from prover and use kind of using the outcome as a relay message. And combining these 2 points, then actually the lower bound is inspired by this protocol by Calder and Leitner for verifying 3-set. And I'm going to summarize what I'm talking about. So here, the main takeaway of this work is unless the setting of the usual space-bounded quantum computation, which BQL is equal to BQUL, if we're talking about like the interactive proof, then turns out the intermediate measurement is very helpful. Means that unless P is equal to NP, this QIPUL is strictly contained in QIPL. And to show such kind of a difference, we define a 3 model of the space-bounded quantum interactive system. So the verifier's action is either use exactly unitary verifiers, or can use intermediate measurement, or can even use reset operations. And we show the lower bound, upper bound of such proof systems. And another thing I only mentioned briefly in this talk is we also define statistical zero knowledge version for the QIPUL. And turns out here, this zero knowledge property is that it's too powerful, it's not too much. So it turns out this zero knowledge property will kill the advantages usually again from the interactions. So the open problem of this work is first, could we type the lower bound in the QIPUL proof system? It's kind of interesting because usually we simulate a single random bits by doing 1 measurement. But here, if we want to simulate something stronger, we need to simulate like the omega log n random coins, use only log n intermediate measurement, or even less. So it requires some new idea. On the other hand, for these 2 models, they are not tight, and classically we know space-bounded interactive proof system just as powerful as the time-bounded case. So we definitely hope for something happen in quantum world about the same thing. The question just it happened for which model? Do we need something that's really strong, or it even can work with something it's a bit weaker? So that's all my talk.